Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The mid-20th century witnessed an extraordinary confluence of chemistry, physics, and biology, all converging on the fundamental question of life's molecular architecture. Within this fervent intellectual environment, the structure of proteins stood as the great unsolved citadel. The 1951 paper by Linus, Robert Corey, and Herman Brownson, titled The Structure of Proteins, Two Hydrogen-Bonded Helical Configurations of the Polypeptide Chain, represents a watershed moment in scientific history. It was a triumph of deductive reasoning, a demonstration that deep understanding of chemical principles could precede and even correct direct, yet ambiguous, experimental observation. This essay will undertake a profound and systematic evaluation of the internal claims, methodologies, and arguments presented within that seminal work, proceeding section by section to illuminate the intellectual machinery that constructed one of biology's most iconic forms. The analysis will focus exclusively on the paper's internal logic, assessing how its authors built their case from foundational axioms to a compelling and ultimately correct vision of protein structure, a vision that would permanently alter the course of molecular biology. Section 1. The foundational postulate of stereochemical rigidity. The paper's entire intellectual edifice rests upon a single, powerful assertion introduced in its opening sections. The polypeptide backbone possesses a defined and rigid geometry. Pauling and Corey established this foundational premise through an exhaustive study of the crystal structures of simple amino acids, dipeptides, and other related small molecules. Their argument, presented with unwavering confidence, was that the amide group, which links successive amino acids, is planar. This planarity arises from resonance, where the carbon-nitrogen bond acquires a significant degree of double bond character, thereby restricting rotation around it. The paper meticulously details the consequences of this feature. It specifies the bond lengths for the carbon-oxygen double bond, the partial double bond of the carbon-nitrogen link, and the other covalent connections within the peptide unit. It further specifies the bond angles around the central alpha carbon and the nitrogen atom. By asserting these precise, unyielding values, the authors dramatically reduced the universe of possible protein conformations. The problem of protein folding was transformed from one of infinite possibility into a discrete puzzle, where stable structures would emerge from fitting these rigid planar units together in a sterically permissible and energetically favorable manner. The evaluation of this initial claim is straightforward. It was entirely correct and methodologically revolutionary. It established a set of non-negotiable chemical rules that any plausible model of protein structure had to obey. This approach, privileging fundamental stereochemistry over the blurry and often misleading X-ray diffraction patterns of complex fibers then available, represents the paper's core philosophical contribution. Section 2. The logical deduction of helical symmetry. Having established the rigid peptide plane as their fundamental building block, Pauling, Corey, and Brownson next addressed the question of how these units would be arranged in a long polypeptide chain. Their central claim in this section is that the most stable arrangement for a chain of identical repeating units involves placing each unit in an equivalent orientation relative to the chain axis. This equivalence of position for each residue logically necessitates a helical structure. The argument is one of elegant simplicity. To maximize stability, the authors posited that hydrogen bonds should form between the carbonyl oxygen of one peptide group and the amide hydrogen of another. For these bonds to form systematically along a long chain composed of equivalent residues, each residue must be spatially related to its neighbours by the same rotational and translational operation. The only geometric form that satisfies this condition is a helix. The paper then proceeds to define a helix with mathematical precision, describing it by two key parameters: the number of residues per turn of the helix, denoted as n, and the axial translation per residue, denoted as T. The brilliance of this section lies in its move from a chemical principle, hydrogen bonding, to a mathematical inevitability, helical symmetry. They argued that any stable, repeating structure within a protein composed of identical amino acid links would almost certainly be helical. This claim provided a powerful theoretical filter, allowing them to search for specific helical structures that also satisfied their strict stereochemical constraints, a far more tractable problem than exploring all of random space. Section 3. The alpha helix, a masterpiece of rational design. This portion of the paper presents the primary fruit of their deductive labor, the alpha helix. This structure is described with extraordinary detail and confidence. The authors systematically searched for helical configurations that allowed for the formation of strong, linear hydrogen bonds while adhering to the planar peptide geometry and avoiding any steric clashes between atoms. Their search yielded a uniquely stable structure, which they termed the alpha helix. They specify its parameters precisely. It is a right-handed helix with a number of residues per turn, n, equal to 3.6. The axial rise per residue is 1.5 angstroms, yielding a total pitch, or the distance of one full turn, of 5.4 angstroms. The paper's key claim is that the stability of this structure derives from its optimized hydrogen bonding network. In the alpha helix, the carbonyl oxygen of a given residue, which can be designated as residue I, forms a nearly perfectly linear hydrogen bond with the amide hydrogen of the residue at position I+4 along the chain. This bonding pattern creates a strong, internally satisfied structure where all backbone amide protons and carbonyl oxygens, excepting those near the ends of the helix, are engaged in hydrogen bonding. The model they built, famously first constructed with folded paper before being rendered with more formal atomic models, showed a tightly packed core with the amino acid side chains projecting outwards, minimizing steric hindrance. The evaluation of this central claim reveals it as the paper's crowning achievement. The proposed alpha helix, later designated the 3.6 sub-13 helix to denote its residues per turn and the number of atoms in the hydrogen-bonded ring, was a structure of profound elegance and chemical soundness. It was a prediction of breathtaking accuracy, a theoretical construct that would be experimentally verified in crystalline proteins years later. With almost no modification, it perfectly embodied their founding principles, demonstrating that chemical logic could indeed unveil nature's designs. Section 4. The gamma helix, a logical, but biologically unfavored counterpart in a demonstration of intellectual thoroughness. Pauling and his colleagues presented a second possible helical structure, which they named the gamma helix. The inclusion of this model serves to highlight the rigor of their systematic search. The gamma helix, like its alpha counterpart, was derived from the same set of stereochemical first principles. It is described as a wider, more open helix with a different set of defining parameters. Its hydrogen bonding pattern involves a link between the carbonyl oxygen of residue I and the amide hydrogen of the residue at position I+5. This results in a helix with approximately 5.1 residues per turn, designated the 5.1 sub-17 helix. The paper presents this structure as another theoretically plausible solution to the problem of arranging polypeptide chains. However, a close evaluation of their own description reveals subtle but critical flaws that render it less favorable. The gamma helix contains a noticeable hole running down its central axis, an energetically unfavorable vacuum in the tightly packed environment of a protein. Furthermore, the geometry of its hydrogen bonds is slightly more strained, deviating from the ideal linearity that conferred such stability upon the alpha helix. The steric interactions between backbone atoms are also less optimal. While the authors presented it as a viable candidate, their own meticulous chemical reasoning implicitly argued against it. The historical reception confirms this internal assessment. The gamma helix is an exceptionally rare structure in nature, appearing only in very short segments under specific circumstances. Its inclusion in the 1951 paper can be viewed with a certain scholarly appreciation for its completeness, a testament to their desire to explore the full range of possibilities allowed by their rules, even those that were less than perfect. It serves as a control group in their logical experiment highlighting by its minor imperfections the supreme fitness of the alpha helix. Section 5, the crucial reconciliation of theory and experimental data. The final masterstroke of the paper lies in its connection of these theoretical models to the existing, albeit perplexing, experimental data from X-ray diffraction of protein fibers, particularly alpha-keratin from sources like hair and wool. For years, the alpha-keratin diffraction pattern, with its characteristic meridional reflection at a spacing of 5.1 angstroms, had defied a clear structural interpretation. Previous models, including those from William Asbury, who pioneered this work, failed to adequately explain it. The claim made by Pauling and Corey in this section is that their alpha helix model provides a complete and satisfying explanation for these long-standing experimental puzzles. They argued that the 5.1 angstrom reflection, which Asbury had interpreted as the residue repeat distance, was something else entirely. In their model, the alpha helix has a pitch, or the height of one full turn, of 5.4 angstroms. They proposed that in keratin, these helices might be slightly tilted or coiled around each other in a coiled coil arrangement, which would shorten the apparent axial repeat to the observed 5.1 angstrom value. This was a brilliant reinterpretation of the data, seeing the major reflection as arising from the helical pitch, a feature invisible to previous models. Furthermore, they pointed to another faint but persistent reflection in the keratin pattern at 1.5 angstroms. This reflection had been largely ignored or considered an artifact. Pauling's model gave it a clear and direct meaning. It was the axial rise per residue along the helix, a fundamental parameter of their alpha helix structure. The evaluation of this section's claims is overwhelmingly positive. It showcases the power of a good theory to make sense of confusing data. They demonstrated that their model was not merely a pretty abstraction, it had real explanatory power, solving a problem that had stumped the field for over a decade. This alignment of their rationally derived structure with previously intractable empirical evidence provided the most compelling argument for the correctness of the alpha helix. In conclusion, the 1951 paper by Pauling, Corey, and Branson stands as an enduring monument to the power of theoretical chemistry in solving biological problems. Its profound and lasting significance stems directly from the integrity and brilliance of its internal claims. Assessed in sequence, the work's foundation upon the rigorously defined planar peptide unit provided an unshakable chemical grammar. From this axiom, the deduction of helical symmetry as the most probable conformation for a repeating polymer was a triumph of logical necessity. This led to the proposal of the alpha helix, a structure whose specific, detailed geometry was presented as a uniquely stable solution, a claim substantiated by its optimal hydrogen bonding and steric comfort. The inclusion of the less stable gamma helix further underscored the exhaustive and unbiased nature of their search. Finally, the masterful reinterpretation of the keratin X-ray data, transforming confusing artifacts into confirmatory evidence for the alpha helix pitch and residue rise, sealed their argument. Every step of their reasoning, from the first stereochemical postulate to the final comparison with experimental reality, formed an unbroken chain of logic. The paper did more than just propose the alpha helix, it championed a new methodology for structural biology, one where the precision of chemical bonding principles could guide discipline and ultimately illuminate the path toward understanding the complex architecture of life itself. Its claims were so robustly constructed and its conclusions so precisely articulated that it provided an intellectual blueprint that would inspire and inform a subsequent discovery of other great biological structures, shaping the very course of molecular science for generations to come.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.